Part 1 Introduction. Earthquakes are among the most dangerous, destructive, and unpredictable natural disasters in the world. Unlike storms or floods, which can often be forecast several hours, even several days in advance, earthquakes usually occur with little or no warning. It's only a few seconds or minutes. Powerful movement between Earth's surface can cause the ground to shake violently, making buildings collapse, roads crack, bridges fail, and the central infrastructure stop functioning. The disaster can lead to enormous economic loss and, more importantly, cause serious injury and large thousands of lives. The level of destruction caused by an earthquake depends on many factors, including magnitude, depth, location, soil condition, and the quality of building in the affected area. In densely populated cities, the consequences become especially severe because a large number of people live and work in high-rise buildings. If these structures are poorly designed or constructed with waste material, they may be not to be able to withstand strong ground motion. As a result, collapse of building one of the main causes of death during major earthquakes. The threat of earthquake is particularly serious in countries located near geological fault lines or long Pacific Ring of Fire. Nations such as Japan, Mexico, Chile, and United States, Indonesia, New Zealand, and Taiwan regularly experience seismic activity. In these places, earthquakes are not considered relevant but ongoing risks that must be carefully managed. Large cities such as Tokyo, San Francisco, Mexico City, Santiago, and Taipei have millions of residents, making earthquake safety an important part of urban planning and construction. To reduce danger, engineers, architects, and scientists have spent many years developing advanced technology that allows buildings to survive strong earthquakes. In the past, people also believed that safe buildings were one of the extremely heavy, solid, and rigid. However, modern engineering has shown that completely rigid structures may easily crack or break when the ground moves suddenly. Therefore, earthquake-resistant buildings are designed not only to be strong but also flexible. Instead of resisting every movement, the buildings are able to sway lightly with the motion of the ground. This flexibility helps prevent the structure from breaking under extreme pressure, as they also special system reduce seismic energy before spread throughout the building. Technologies such as a base isolation, shock absorber, tools, mat damper, reinforced steel frame, and flexible joint can greatly limit the impact of strong vibration. Base isolation system, for example, separates a building from the moving ground by placing special rubber and steel bearing underneath it. When an earthquake occurs, the ground may move strongly while the upper building remains relatively stable. Other buildings use larger dampers that function like shock absorber in vehicle, reducing movement and helping the structure return to its original position. Thanks to the innovation, many modern skyscrapers and public buildings can remain standing even during powerful earthquakes. Although no building can be made completely earthquake-proof, careful design and advanced technology can significantly reduce damage, protect human life, and allow cities to recover more quickly and after disaster. The earthquake-resistant structure demonstrates how science, engineering, and architecture can work together to create safer living environment in regions where seismic activity is a constant threat. Part 2. How earthquake-resistant buildings work. When earthquakes occurs, the ground can move in several different directions. It may shake from side to side, move forwards and backwards, or rise and fall vertically. This sudden movement creates powerful forces that travel from the ground through building foundation and its main structure. If a building is too rigid, it cannot adjust to its movement. As a result, the seismic forces are transferred directly to its column, beam, floor, and wall, increasing the risk of crack, deformation, or total collapse. For this reason, earthquake-resistant buildings are not designed to remain completely motionless. Instead, they are built with enough flexibility to move slightly during strong ground shaking. Although this movement may seem dangerous, it actually helps protect the building. A flexible structure can absorb, distribute, and release seismic energy instead of allowing a full force the earthquake to concentrate in one area. One of the most important technologies used in earthquake-resistant construction, the base, is isolation system. This system separates the main structure of the building from the ground by placing special bearing between the foundation and upper parts of the building. The bearings are often made layer rubber, steel, or other flexible material. When the ground moves, the isolator surrounds foundation to shift while reducing the amount of motion transferred to the building above. As a result, the upper floor experiences much less shaking. Another common technology is the use of seismic dampers. These devices work in a similar way to the shock absorber found in the car. They absorb part of the earthquake's energy and reduce speed and intensity of the building movement. Dampers may contain oil, steel, rubber, or other energy-absorbing material. They are usually installed between floors, inside the structural frame, or near important joint. By controlling excess movement, dampers help protect both the main structure and the people inside the building. Flexible steel frames are also widely used in modern earthquake-resistant buildings. Steel but blend with breaking easily during earthquake, steel column and beam can move slightly while continuing to support the weight of the building. Engineers carefully design frames to escape the control way. This prevents sudden structural failure and allows the building to remain standing even after strong shaking. Some tall buildings also use a large device called the two-mass damper. It's usually a heavy steel or concrete weight installed near the top of the building. When the structural weight is in one direction, the damper moves in the opposite direction. This counter movement reduces building motion and helps restore its balance. Two smart dampers are especially useful in skyscrapers, which can sway significantly during earthquakes or strong wind. In addition to technology, engineers reinforce concrete, cross-spacing systems, shear wall, flexible connection, and deep foundation. Each component plays a different role in strengthening the building and controlling how seismic forces travel through the structure. The main principle of earthquake-resistant design, therefore, not prevent all movement but to manage it safely by combining strength, flexibility, balance, and energy absorption. Modern building can greatly reduce structural damage. This system protects human life, prevent complete collapse, and make it easier for city recover after major earthquake. Part 3. Taipei's 101 in Taiwan. Taipei's 101 is one of the most famous skyscrapers in the world. Not only because of its impressive height and distinctive appearance, but also because of its advanced ability to resist earthquakes and powerful wind. Located in Taipei, the capital city of Taiwan, the building stands in an area that frequently experiences earthquakes, typhoons, and other extreme weather conditions. Taiwan lies near several active tectonic plate boundaries, makes seismic activity constant concern for architect, engineer, and city planner. When Taipei's 101 was designed, one of the great challenges was to create a structure that could remain stable and both strong ground motion and several wind pressure. Tall buildings are particularly vulnerable because their height causes them to sway more noticeably than shorter structures. During a major earthquake or typhoon, the upper floor that skyscrapers may move significantly, creating its occupant as placing enormous stress on the building structural component. To solve this problem, the engineer of Taipei's 101 installed one of the largest and most well-known tuned mass dampers in the world. A tuned mass damper is designed to reduce excessive movement in tall buildings. The most remarkable part of Taipei's 101 system is the huge steel frame suspended near the top of the tower between the 87th and 92nd floor. The enormous golden sphere has a diameter of approximately 5.5 meters and weighs about 606 metric tons. It's made from several thick steel plates that has been carefully welded together. The sphere is expanded by a strong steel cable that connected to large hydraulic devices that help control its movement. Unlike many structural systems that are hidden inside a building, the dampers in Taipei's 101 is visible to visitors, making it both important safety feature and popular tourist attraction. The dampers work through a relatively simple but highly effective principle. When strong wind and earthquakes push the tower in one direction, the heavy steel frame moves in the opposite direction. This counter movement helps balance the building and reduces arm of swaying experienced by structure. For example, if the upper part of Taipei's 101 begins to move to the left, the damper shift towards the right. The shift of the completely to stop the building from moving because a certain amount of flexibility is necessary for safety. Instead, it controls the motion and prevents the tower from swaying too far too quickly. In this way, the two mesh dampers act like a giant shock absorber. The movement of sphere also helps absorb and relieve some of the energy produced by strong wind and seismic vibration. Hydraulic dampers attached to the system slow down the sphere movement and prevent it from swinging uncontrollably. This allows the device to reduce the tower motion gradually and safely. Thanks to the system, the swaying of Taipei's 101 can be reduced significantly. People working, shopping, or visiting the building are therefore less likely to experience severe dizziness or discomfort during storm or minor earthquake. At the same time, the reduction in movement protects important structural or non-structural parts of the tower including wall, window, elevator, pipes and electrical system. However, the giants still fear only one part of Taipei 101 earthquake-resistant design. The building also relies on extremely strong structural framework. Its foundation is supported by hundreds of reinforced concrete piles driven deep into the ground. These piles reach stable layers of rock beneath the softer soil and have anchored the skyscraper securely. Taipei 101 also contains a strong reinforced concrete central core. This core supports much of the building weight and provides resistance against twisting and bending. It contains important facilities such as elevator, staircases, and emergency routes. During an earthquake, the central core helps distribute seismic forces throughout the structure instead of allowing them concentrable in one vulnerable area. In addition, the skyscraper uses 8 enormous main columns about the structure. These columns are made from high-strength steel and reinforced concrete. They are connected to the central core by horizontal structural element known as outrigger trusses. This system allows the outer column and the inner core to work together, increasing the strength and stability of the entire tower. Flexible steel framing is another important part of the building design. Steel can bend, deform slightly without breaking, making it highly suitable for earthquake-resistant construction. During strong shaking, the steel frame of Taipei's 101 can move in a controlled manner while continue support the building the normal way. The tower safe also contribute the safety. Taipei's 101 will inspire traditional Asian pagoda and bamboo plan. Its top section with building a unique appearance but also have reduced the winds. The design prevents winds from flowing smoothly around the tower in building up its exposure. The engineering achievement of Taipei's 101 has been demonstrated during several natural events. The tower has experienced earthquakes and powerful typhoons while remaining structurally stable. Its dampers have sometimes moving dramatically during severe weather, showing how actively the system worked to protect the building. Although no skyscraper can be completely protected from every possible natural disaster, Taipei 101 shows how advanced engineering can greatly reduce risks. Its turn mass damper, this foundation, reinforced concrete core, massive supporting column, flexible steel frame, and carefully designed and shaped all work together completely safety system. Taipei 101 is therefore more and simple of Taiwan economic growth and architectural ambition. It is also an outstanding example of how technology, design, and scientific knowledge can help the human adapt to dangerous natural conditions. By combining strength with flexibility, the tower demonstrates that modern skyscraper can be both visually impressive and highly resistant to earthquake and storm. Part 4. Tokyo skyscrapers in Japan. Japan is one of the countries most frequently affected by earthquakes because the nation is located near several active tectonic plate boundaries. Earthquakes occur regularly in many parts of the country. Some are small and cause little damage, while others can be powerful enough to destroy buildings, damage transportation systems, and threaten millions of people. For this reason, earthquake safety has become an essential part of Japanese architecture, engineering, and urban planning. Buildings in Japan must follow strict construction standards, especially tall structures located in densely populated cities. Engineers are required to consider not only the weight and height of the building, but also its will respond to sudden horizontal and vertical ground movement. Modern Japanese structures are therefore designed to bend, sway, and absorb seismic energy without collapsing. One of the most impressive examples of earthquake-resistant engineering in Japan is Tokyo Skyscraper. Located in Tokyo, it is a major broadcasting and observation tower as well as the most recognized landmark in the country. Its main purpose is to transmit television and radio signals, but it also contains observation deck, shop, restaurant, and tourist facility. Because of enormous height, Tokyo Skytree and had designed with exceptional durability. Tall towers are particularly vulnerable during earthquakes because movement base can become much stronger near the top. Strong wind can also cause high structural weight. Therefore, the engineers to respond for the Tokyo Skytree need to create a system that could reduce movement caused by both sides activity and extreme weather. The earthquake-resistant design Tokyo Skytree with the inspired traditional Japanese wooden pagoda. Many ancient pagodas in Japan have survived for hundreds of years despite being pushed under numerous earthquakes. This is remarkable because they were constructed long before modern engineering technology and reinforced concrete existed. Researchers discovered that one of the main reasons for their durability was the newest way that structural components moved during the earthquake. Traditional pagoda often contain a central known as the Shinbashira. This is pillar extend vertically to the center of the structure and can move somewhat independently from the surrounding floor and wooden frame. When an earthquake shakes the ground, the different levels of the holder do not all move in exactly the same direction at the same time. Instead, they sway with a certain degree of independence. The center pillar helps control balance movement. As one part of the structure shifts in one direction, another part may move in the opposite direction. This reduces the concentration of the seismic forces and prevents the entire building from becoming unstable. The engineers of Tokyo Skytree adapted traditional principles and combined with modern construction technology. At the center of the tower, the massive reinforced concrete column. This central column structurally separates from much of the outer steel framework, allowing the two parts to respond differently when the tower is shaken. During an earthquake, the outer steel structure may begin to sway in one direction, while the reinforced concrete core moves with different rhythm or in opposite direction. The opposing movement can help gain a part of the earthquake energy. As a result, the overall shaking of the tower reduces. This system works in a similar way to a balancing mechanism. Instead of forcing entire tower to remain completely rigid, it's allowed to control movement. This is important because an extremely stiff structure may crack or break when exposed to powerful forces. A structure that can move and can carefully designed way is often better able to survive to strong seismic activity. A central column also acts like a large internal damper. Its weight and movement help slow down swaying of surrounding steel frame. Special connection and energy absorbing designs assure managed interaction between the core and exterior structure. Together, the components help protect the tower from excessive bending and vibration. The outer framework of Tokyo Skytree and makes primarily from high-strength steel. Steel is extremely useful in earthquake-resistant construction because it combines strength with flexibility. It can bend under pressure and return to its original shape without breaking immediately. This gives the tower the ability to absorb energy while continuing to support on weight. The shape of Tokyo Skytree also contributes to stability. The base has a broad, triangular form that gradually changes as the tower rises. Higher sections become more circular, creating a transition have distribute structural forces more evenly. The wide base provides strong support, while the narrow section reduces wind pressure. In addition to the central damping system and flexible steel framework, Tokyo Skytree uses deep foundation to remain security connection to the ground. The foundations were carefully designed to support the tower's enormous weight and resist movement in the soil. This is especially important in Tokyo, where ground conditions can vary and strong earthquakes may cause significant shaking. The tower is also equipped with monitor system that allow engineers to observe its movement. Sensors can detect changes in vibration, structural stress, and wind pressure. These systems provide valuable information about how the tower behaves, earthquake, and storm. They also help maintenance teams identify possible problems before they become serious. Tokyo Skytree represents an impressive combination of traditional knowledge and modern science. Its designer is not complete structure of ancient pagoda. Instead, they studied the principle that makes buildings stable and adapt them to a much taller and more complex modern tower. This approach of the traditional architecture can provide valuable lessons for contemporary engineering. Ancient Japanese builders may not have had computers, advanced machinery, or modern materials, but they understood that flexibility, balance, and control movement were essential in earthquake-prone regions. Today, Tokyo's Skytree stands as both a technological achievement and a cultural symbol. It demonstrates Japan's ability to respect its architectural heritage while developing innovative solutions for modern cities. The combination is reinforced concrete central column, flexible steel frame, deep foundation, special damping system, and carefully planned shape make it one of the world's remarkable earthquake-resistant structures. More importantly, Tokyo Skytree proves that buildings do not always need to fight against natural forces. completely resilient by moving swiftly, allowing structural parts to balance one another. A tower can reduce damage and remain stable. Through this intelligent combination invention, demonstrating advanced technology, Kyoto Skytree had become a powerful symbol of safety, creativity, and earthquake-resilient design in Japan. Past 5, Mori Tower in Tokyo. Mori Tower is one of the most prominent high-rise buildings in Tokyo and forms the central feature of the Roppongi Health Complex. Located in one of the city's busiest commercial and cultural districts, the tower is used for a wide variety of purposes, including offices, shops, restaurants, exhibition spaces, and tourist attraction. Thousands of employees, visitors, and local residents pass through the building and surrounding facility every day. However, Mori Tower is not only known for its high modern experience and convenient location, it is also considered an important example of disaster-resistant architecture in Japan. Since Tokyo is frequently exposed to earthquakes, typhoons, strong winds, and other natural hazards, the building was designed to protect the people inside it. More importantly, it's worth planning to continue supporting essential activity even after major disaster. One of the main features of Mori Tower is its advanced earthquake-resistant structure or system. During an earthquake, seismic energy travels from the ground to the building foundation and into column, beam, walls, and floor. If this energy is not carefully controlled, the building may experience successive upwelling, deformation, cracking, or damage to important equipment. To reduce this risk, Mori Towers uses several types of damping devices. These devices are installed in different parts of the building and are designed to absorb parts of the energy created by seismic vibration. Their function is similar to that of shock absorber in a car. When the ground moves suddenly, the dampers have slowed down and controlled movement of structure. Instead of allowing all the earthquakes force to pass directly through the building, the damping system converts part of the motion into the other form and vanishes energy such as heat. This reduces the pressure placed on the main structure of component. As a result, the column, beam, joints, and walls are less likely to suffer serious deformation. The dampers also have reduced movement between different floors. In a tall building, its floor may respond slightly different during an earthquake. If the difference in movement to become too large, walls may crash, windows may break, and private electrical system may be damaged. By limiting this movement, Mori Tower damping technology helps maintain the overall stability of structure. The building's strong structural frame also plays an important role in earthquake protection. High-strength steel and reinforced concrete are used to create structures that are both strong and flexible. Rather than remaining completely rigid, the tower can move slightly during strong shaking. This controlled flexibility allows to distribute seismic forces more safely throughout the building. Another important element is the tower foundation. A high-rise building of this size requires deep and carefully adjusted foundation to support in an enormous way. The foundation helps transfer to the building load into the stable layer beneath the ground and reducing the danger of uneven during an earthquake. However, Morris Tower's disaster prevention strategy go far beyond protecting the physical structure. The building will also designed to function as temporary shelter and support center during an emergency. This is particularly important in densely populated cities such as Tokyo, where transportation systems may stop and many people may be unable to return home immediately after a major earthquake. For this reason, Moritara is equipped with emergency power system. If the main electricity supply is interrupted, backup generator can provide power for a central facility. These may include emergency lighting, communication equipment, fire safety system, water pump, and select elevator. Maintaining electronics allow the building to continue operating safely and prevent complete darkness or confusion during emergency. The tower also has systems for storing and supplying water. After a strong earthquake, public water network may be damaged to temporarily unavailable. Having an independent emergency water supply helps meet basic needs such as drinking, sanitation, and cleaning. Water is also essential for fire protection, especially if fire break out after an earthquake. In addition, emergency foods, medical supplies, blankets, and other essential items can be stored with the complex. These supplies are intended to support people who may need to remain in the area for several hours or even several days. Such preparation is extremely valuable because road, railway, and community communication systems may take time to recover after a major disaster. Open spaces around the Republic Hill complex may also serve as gathering or evacuation area. During emergency, these spaces can provide a safer places for people to assemble, receive information from whisper assistance. Clear emergency routes, signed communication system, and trained staff are also necessary to guide people and prevent panic. More towers therefore is flexible, understanding disaster-resistant architecture. An earthquake-resistant building should not only avoid collapse, it should also protect the occupant, maintain essential services, support emergency operation, and contribute to the recovery of the surrounding community. This concept is especially important for larger urban development. If a major building remains standing but loses power, water, communication, and emergency support, it may still become unsafe or unusable. Moist Tower addresses problem by combining structural strength with our operational preparedness. The building demonstrates that modern disaster planning requires cooperation between architect, engineer, emergency planners, building manager, and local authority. The structural system must be supported by backup resources, evacuation plan, regular inspection, and emergency training. Every part of the system must work together when a disaster occurs. Mori Tower, therefore, more than a modern for a commercial skyscraper. It exemplifies how a large building can become an important part of the city emergency infrastructure. Its dam defines a strong structural frame, deep foundation, backup electricity, water supply, storage necessity, and shelter area all contribute to its ability to protect and support people. Through design, more towers show that successful earthquake with the system architecture is not measured not only by whether building remain standing. It is also measured by whether the building continue provide safety, communication, water, power, and basic support after the shaking hard start. The combination of structural resilience and emergency preparedness make Mori Tower an outstanding, more disaster urban architecture in Japan. Part C. Torre Mayor is Mexico. Torre Mayor is one of the most recognizable skyscrapers in Mexico City, an important example of earthquake-resistant architecture in Latin America. The building stands along Paseo de la Reforma, one of the capital's busiest and most important avenues, and contains offices and commercial spaces and represents growth modernization of Mexico City. However, construction such tall building its location require engineers to overcome several serious geological challenges. Mexico City is highly vulnerable to earthquakes because it's affected by seismic activity from tectonic zones located along Mexico's Pacific coast. Although many earthquakes epicenters are located hundreds of kilometers away from the capital, the vibration can still cause severe damage when they reach the city. One of the main reasons is the unusual ground beneath much of Mexico City. Larger parts of the city were built on the soft sediment of ancient lakebed. This soil much weaker solid rock and can amplify seismic sway. When earthquakes vibration reach lake, the soft soil may increase the duration and intensity of the shaking. It can also cause different parts of the ground to move unevenly. For tall buildings, this creates a especially dangerous situation because the movement at the upper floor may become much greater than movement near the foundation. To reduce the risk, Torres Mayor will design with a sophisticated seismic protection system. One of the most important features is the network damming device installed throughout the building structural frame. These dampers are designed to absorb to control the energy produced by earthquake. The damping system works in a manner similar to the shock absorber used in vehicle. When a car passes over the rough surface, shock absorber reduce sudden movement and prevent the vehicle from bouncing excessively. In turn, the damper performs a similar function on a much larger scale. When the ground moves, the tower begins to sway, but the dampers absorb significant parts of the seismic energy and help slow motion, rather than allowing earthquake forces travel freely to the building. The dampers reduce stress on the column, beam, joints, and floor. This helps limit the amount of the deformation that occurs between different levels of the tower. Excessive movement between floors can damage wall, window, electrical system, elevator, and water pipe. By controlling this movement, the damping system helps protect both the main structure and the interior component of the building. Torre Mayor is not designed to remain completely motionless during the earthquake. In fact, a certain degree of movement is necessary. A structure that's too resist may crack or fail suddenly when it is exposed to powerful forces. Torre Mayor is therefore designed to way to control manner. Its movement is carefully calculated so that the tower can release energy without losing stability. The steel frame of the building is another central element of earthquake-resistant design. The steel is particularly valuable in seismic construction because it combines strength with ductility. Ductility is the ability for a material to bend, stretch, or change shape without breaking immediately. During a strong earthquake, some structural component may temporarily be formed. Instead of snapping under pressure, the steel member of Tory Mayer can bend to a limited degree while continuing to carry building weight. This controlled deformation helps prevent sudden collapse. It also gives structure more time to respond to changing seismic forces. Engineering carefully determined where deformation could occur safely. Certain structural elements were designed to absorb energy while protecting more critical parts of the building. This approach allowed the tower to remain stable even some components experience temporary stress or minor damage. The foundation of Torres Mayer was also designed to respond to Mexico City's difficult soil conditions. This foundation element helped transfer the weight of the building to stronger layers beneath the soft ground. The foundation must support the enormous vertical weight of the tower while also resisting horizontal movement during earthquake. The building structure system functions are completely networked rather than collection of separated parts. Its foundation, column, beam, steel braces, damper, and floor system work together to distribute earthquake forces. If one area experiences pressure, the system helps transfer parts of the force to other sections of the building. Tory Mayer has been tested by real earthquake happen and demonstrates effectiveness of its design. During seismic activity, the building has been able to sway to suffering catastrophic structural failure. This performance has strengthened its reputation as one of the most advanced earthquake-resistant skyscrapers in the region. The importance of Tory Mayer goes beyond architectural appearance. It shows how modern engineering can make tall buildings safer even in cities with difficult ground conditions. Rather than avoiding movement completely, the building is designed to control movement, absorb energy, and prevent sudden failure. Tory Mayer therefore considered a major achievement in Latin American construction. Its advanced damping system, flexible steel frame, deep foundation, and carefully planned structural connection allow in response safely to strong earthquake. The tower demonstrates that with proper engineering, high-rise building can be constructed in earthquake-prone regions while still providing a high level of safety for occupants. Part 7. Torre is famous in Mexico. Another outstanding earthquake-resistant building in Mexico City is Torre Reforma. Located on Paseo del Reforma, Skyscraper is known for its unusual form, modern appearance, and innovative structure system. From a distance, the building resembles a giant chisel rising into the sky. Its shape is created by two enormous concrete walls that extend along its side of the tower. These concrete walls are not simply decorative features. They serve as the main structural support for the building and function like a powerful skeleton. Together, they carry a large portion of the tower weight and resist the forces produced by earthquakes and strong winds. Designing tourist reformer was particularly challenging because of Mexico City's short story and high seismic risk. As with Torre Mayor, earthquake waves can become stronger, and when they pass through the sediment it sinks and lakes within the city. For this reason, the building had to be able to survive long periods of intense shaking without experiencing sudden structural failure. The two main concrete walls play a central role in solving this problem. Concrete is strong under the compression, meaning it can support enormous vertical loads. The walls have carried the weight of the floor, equipment, furniture, and occupants. At the same time, the design and position provide resistance against horizontal movement. During an earthquake, the ground pushes the building from side to side. The concrete walls have controlled this motion by providing stiffness and stability. However, the building is not completely rigid. Its structural system is designed to allow certain areas to bend and firm in a controlled way. One of the most visually distinctive features of the Torre reformer is the pattern of the opening found in the concrete wall. The opening may appear to be part of the architectural design, but they also have an important engineering function. Their location, size, and shape were carefully calculated. The opening helps control how forces move through the wall. They allow engineers to determine where the structure may bend during earthquake and how energy will be distributed. Without the opening, the wall might be too stiff in certain areas, causing cracks to develop unpredictably. By creating carefully positioned opening, designers were able to guide deformation towards safer parts of the structure. This means that the building is designed to respond to seismic forces in the planned sequence. Instead of falling suddenly, some sections may flex or crack in the controlled manner. This helps release earthquake energy and prevent it from becoming concentrated in one critical location. Such controlled deformation is an important principle in earthquake-resistant engineering. The goal is not necessarily to prevent all damage. In an extremely strong earthquake, minor structural or non-structural damage may be unavoidable. The main objective is to prevent total collapse and protect human life. Torre reformer structural system help provide occupants with more time to evacuate if necessary. Sudden collapse is one of the great dangers during the earthquake because it gives people little opportunity to escape. A ductile structure that stands gradually provides a much higher level of safety. The floor of Torre reformer can connect it to the main concrete wall and other supporting elements. The connection allows earthquake forces to be transferred to the building and distributed across the entire structural system. Steel elements are also used to provide additional flexibility and support. The building foundation is another important component. Because of the ground beneath Mexico City can move unevenly, the foundation must prevent excessive settlement and keep the tower balanced. Deep structural elements help anchor the building and transfer its weight to more stable soil layer. Torre reformer were also designed with efficiency and sustainability in mind. Its shape allows natural light to reach many interior spaces, while the building structure reduces the need for excess internal column. This creates larger and more flexible offices area. The tower demonstrates that safety does not have to limit architectural seismic activity, its unusual shape is directly connected to its structural performance. The massive wall created a dramatic individual identity while also serving as the main defense against earthquakes. This combination of form and function and the more impressive quality of terrain reformer. The building does not hide the structure. Instead, the structural world becomes a major part of this appearance. Visitors can clearly see that the tower design is based on strength, stability, and controlled movement. Terrain reformer that is therefore an excellent example of modern earthquake-resistant architecture. It shows how engineers can use concrete walls, carefully planned opening, flexible connection, and deep foundation to create a building that is both visually unique and structurally safe. More importantly, the tower demonstrates that earthquake-resistant design not only about making a building strong, it is also about understanding how the building will move when it may bend, and how its components will work together during a disaster. Through this intelligent use of structure and architecture, tourist reformer have become one of the Mexico City's most remarkable modern buildings. Part H, Transmedical Pyramid in the United States. The Transmedical Pyramid is one of the most famous landmarks in San Francisco, California. With its tall, narrow, pyramid-shaped front, the building is immediately recognizable as having become an important part of the city's skyline. Although its shape was originally considered unusual, it is now admired as a creative example of modern architecture. San Francisco is located near several major geological faults, including the San Andreas Fault. Because of this location, the city faces a constant risk of powerful earthquakes. Past earthquakes have caused serious damage to buildings, roads, bridges, and public services. Therefore, earthquake resistance is a central consideration in the design of high-rise buildings in the region. The Transmedical Pyramid was designed with both structural safety and architectural identity in mind. Its wide base and gradually narrowing upper section have created stable form. Most of the building mass concentrate closer to the ground, while the upper level is small and lighter. This distribution of weight provides several advantages. First, the broad space helps support the vertical load of the building. Second, the light of upper section reduces the force created when the structure weighs. During an earthquake, heavy upper floor can generate strong movement and places significant pressure on the lower structure. By gradually reducing fault side toward the top, the measured shape help control this effect. The building distinctive form also help distribute forces more efficiently. Earthquake force is controlled through the sloping structure towards the wider lower section. This does not eliminate movement, but it helps reduce the concentration of stress at the top of the tower. Inside the the pyramid is reinforced structural framework designed to provide strength and flexibility. The building includes a strong system of steel and concrete components that support weight and resist horizontal forces. During earthquake, these elements work together to prevent the tower from twisting or bending excessively. The building's frame not completely rigid, like many modern earthquake-resistant structures. It is designed to move slightly, Controlled movement allows the building to absorb and release seismic energy. If structure were unable to move, powerful forces could cause sudden cracking or failure. The lower section of the building includes additional structural reinforcement. This area must support the weight of all the floor above while also resisting the strongest forces during shaking. The wide bay provides more space for column, braces, and other supporting components. The foundation of the transmaterial pyramid is also essential to its stability. The building is supported by a deep foundation system that helps the anchorage to ground. This foundation distributes the tower weight and reduces the risks of uneven settlement. During an earthquake, the foundation must respond to rapid ground movement. It must be strong enough to remain stable, but also work its upper structure as its weight. If the foundation and the building move in completely different ways, serious damage may occur. The transmatic pyramid was therefore designed an integrated structural system. Another important feature is use internal bracing. Bracing elements help prevent the building from changing shape excessively. They connect different parts of the frame and allow forces to be transferred across the structure. When the building is pushed in one direction, the braces help distribute the load to other parts of the frame. This reduces pressure on individual column and beam. It also helps the building return toward its original position after the shaking start. The transmatic pyramid has experienced major earthquake activity during history. Its ability to withstand seismic movement has demonstrated the importance of safe internal structural system. During strong shaking, the building may waste, but its movement is part of the design. People inside the tall building may notice the upper floor moving during earthquake. Although this can feel alarming, controlled weighing is often safer than completely rigidity. The structure is designed to move within specific limits without losing its ability to support with weight. The transmaterial pyramid is an excellent example of how architectural form can contribute to structural performance. Its shape is not only visually impressive but also helps distribute weight, reduce upper level mass, and manage earthquake forces. At the same time, its reinforced frame, strong foundation, internal bracing, and flexible structural connection provide additional protection. These features work together to reduce the risk of collapse. The building shows that earthquake-resistant architecture does not always require visible mechanical devices such as giant dampers. Sometimes the overall form of the building, combined with a carefully designed structural system, can play an equally important role. The transmatic pyramid remains one of San Francisco's most iconic buildings. It represents the successful combination of creativity, engineering, and disaster awareness. Its pyramid shape gives the city a unique architectural symbol, while the structural design helps it respond safely to the earthquake risk of the region. Part 9. Shanghai Tower in China. Shanghai Tower is one of the tallest and most impressive skyscrapers in the world. Located in the Lujia financial district of Shanghai, China, the building rises high above the surrounding city and forms part of the group of major skyscrapers. It is used for offices, hotels, observation areas, shop, and other commercial activity. The tower is famous for its twisting form. From the base to the top, the exterior gradually rotates, creating a smooth, pliable state. This design gives the building a modern and futuristic appearance, but it also serves several important engineering purposes. One of the greatest challenges in the designing extremely tall building is controlling wind. At great height, winds can create strong pressure and causes a tower to sway. Even if the building is structurally safe, too much movement can make occupants uncomfortable and may damage window, wall, elevator, or mechanical system. The twisting shape of Shanghai Tower helps reduce the effect. Instead of allowing wind to strike off flat surfaces directly, the curved and rotating exterior guides area around the building. This reduces formation of strong wind forces and limits the amount of pressure placed on the structure. By reducing wind load, the tower requires a less structural material that a building with a less efficient shape may need. The twisting design therefore contributes to both stability and construction efficiency. However, wind is not the only force that Shanghai Tower must resist, but the building must also be prepared for earthquake and other ground movement. Because of its enormous height, even small movement near the base can cause significant wave near the top. To control this motion, Shanghai Tower is used a large 2 mesh anchor installed near the upper section of the building. This device is designed to reduce movement caused by wind and seismic vibration. The dam contains extremely heavy mass that can move independently from the main structure. When the tower sways in one direction, the mass moves in the opposite direction. This counter movement helps balance the building and reduce the intensity of the motion. The system does not stop the building moving completely. Instead, it controls speed and distance of the movement. This is important because some flexibility is necessary for a tall building. The dampers help ensure that a tower remains within a safe movement limit. The two smart dampers also improve comfort for people inside the building. Without such a system, occupants on the higher floor might feel significant motion during strong wind. By reducing swaying, the damper makes the tower more comfortable and protects sensitive equipment. Shanghai Tower structural system consists of several major components working together. At the center is a reinforced concrete core. This core contains elevator, stair, service system, and emergency room. It also serves as the main vertical support for the building. Around the core, large columns that help carry the weight of the tower. This column is connected to the central core to the strong structural element. This connection allows the core in the outer support to share load. When the building experiences with wind earthquake forces, the structural system distributes these forces across multiple components. Instead of allowing one part to carry all the pressure, the tower transfers load between the core, column, floor, and connecting structure. The building is also divided to the several vertical zones. These zones are connected by structural floor schematical level and strengthen the tower. They help reduce excess movement and provide additional support. Another important feature is the double-layer exterior. Shanghai Tower had an inter-building structure surrounded by an outer glass surface. The space between these two layers forms larger internal area and help improvement environmental performance. The outer layer also affects how wind moves around the building. Its curved shape contributes to the tower's aerodynamic performance. At the same time, the double skin system helps control temperature and reduce energy use. The foundation of Shanghai Tower is designed to support the enormous weight of skyscraper. Deep piers extend far beneath the surface to reach stronger ground layer. Above them is a massive reinforced foundation platform that distributes the building's load. This strong foundation is especially important because a tower of height creates tremendous pressure on the ground. It must remain stable under normal conditions and during earthquake. Shanghai Tower also contains advanced monitoring system. Sensors can measure movement, wind pressure, vibration, structural stress, and temperature. Engineers can use this information to evaluate the tower performance and identify changes over time. Such monitoring is essential for modern skyscrapers. It allows building managers to inspect the structure after strong wind and earthquake and determine whether repairs are necessary. The success of Shanghai Tower comes from the combination of many different design strategies. Its twisting shape reduces wind pressure. Its two mass damper controls weighing. Its concrete core, loud column, structural connection, and reinforced floor distribute forces throughout the building. Its deep foundation keeps the tower stable, while sensors allow continued observation. Shanghai Tower therefore represents a highly advanced form of modern engineering. It demonstrates that the safety of skyscrapers depends on more than one protective feature. Every part of the building must contribute to its performance. The tower is also an example how architecture and engineering can support each other. Its spiral form creates a dramatic visualized identity, but the shape is also connected to wide resistance structural efficiency. Although no building can be completely protected from every natural disaster, Shanghai Tower is designed to reduce movement, prevent serious structural damage, and protect occupants. It shows how innovative design, advanced material, and modern technology can make extremely tall buildings safer in challenging environmental conditions. Together, Tory Mayor, Tory Reformer, the 10 medical pyramids and Shanghai Tower demonstrate different approaches to earthquake-resistant design. Some rely heavily on damping systems, while others use flexible steel frames, massive concrete walls, aerodynamics forms, or strong foundation. Despite these differences, they share one important principle: a shaped building must be able to control movement, distribute forces, and absorb energy rather than simply resisting natural forces with complete rigidity. Part 10. The importance of flexible material. Choosing the right material is one of the most important factors in earthquake-resistant constructions. A building must be strong enough to support its weight, but it must also be flexible enough to move without suddenly breaking when the ground shakes. For this reason, engineers carefully study how different materials behave under pressure, bending, stretching, and repeated vibration. Steel is widely used earthquake-resistant building because it has high strength and excellent flexibility. Unlike brittle material that may crack without warning, steel can bend or change shape to a certain degree before it fails. This ability is known as ductility. During an earthquake, a steel beam and column can absorb part of the seismic energy by bending slightly while continuing to support the building. Controlled deformation helps prevent sudden structural collapse and gives occupants more time evacuation if necessary. Reinforced concrete is another central material. Concrete is very strong, it's well compressed, making it suitable for foundation, column, floor, and structural work. However, ordinary concrete is relatively weak when it is stretched or bent. To solve this problem, steel bars are placed inside the concrete. The steel reinforcement increases the ability to resist tension, bending, and cracking. When concrete and steel are combined correctly, they create a structure that is both strong and flexible. The concrete carries much of the building weight, while the internal steel bar have structure remain stable during movement. However, the quality of material in construction is extremely important. With concrete, poorly connected steel bar or incorrect construction method can significantly reduce earthquake resistance. Modern buildings may also use advanced materials such as shape memory alloys. These materials can return to the original form after being bent or deformed. Some structures also contain replaceable components designed to absorb earthquake damage. After the disaster, these parts can be removed and replaced without rebuilding the entire structure. Such technology can reduce repair costs and shorten the periods during which a building must remain closed. Part 11. Base isolation system. Base isolation is considered one of the most effective technologies for protecting buildings from earthquake. In a traditional building, the main structure is connected rigidly to the foundation. When the ground moves, seismic vibration travels directly through the foundation into the column, wall, and floor. A base-isolated building is designed differently. Flexible devices are installed between the foundation and the upper structure. The isolators may be made from alternating layers of rubber and steel, or they may use special sliding material. Their purpose is separate to the movement of the building from the movement of the ground. When an earthquake occurs, the ground and the foundation may move strongly, but the isolator absorbs and reduces parts of the energy before it reaches the main structure. The building above can move more slowly and smoothly, which greatly decreases shaking on the upper floor. This helps protect column, wall, window, furniture, equipment, and the people inside. Rubber bearing among the most common base isolation devices. The rubber allows horizontal movement, while the steel layer supports the heavy weight of the building. Some systems also use curved, sliding surfaces that allow the structure to move during an earthquake, can then gradually return to its original position. Base isolation is often used in hospitals, emergency response centers, government offices, museums, and other important facilities. These buildings must remain safe and operational after disaster. For example, hospitals need to protect patients, medical equipment, water system, and emergency electricity. Even if a hospital does not collapse, intense shaking could damage machine and interrupt medical treatment. Although base isolation can increase the initial construction cost, it provides significant long-term benefits. It reduces structural damage, protects valuable equipment, lower repair expenses, and allow buildings to reopen more quickly. Therefore, it is often considered a valuable investment in both human safety and economic protection. Part 12. Let's inform earthquake-resistant building. Earthquake-resistant building around the world so that humans cannot stop natural disasters, but they can reduce their consequences through science, technology, and careful planning. The safety of the building does not depend only on thick walls, large columns, or heavy materials. It also depends on how the entire structure responds to ground movement. Successful design usually combines several protective systems. Strong foundation provides stability, while flexible thin frame allow control of movement. Reinforced concrete wall supports heavy load. Dampers absorb seismic energy, and base isolation system reduce the amount of vibration entering the building. Emergency power, water supply, communication system, and safe evacuation routes are also important. No single solution is suitable for every structure. The appropriate design depends on the height and purpose of the building, the local soil condition, the expected earthquake risk, and the available budget. A skyscraper may require a large mass damper, while a hospital may benefit more from base isolation. Older buildings may need additional braces, stronger walls, or reinforced columns. Regularly inspection and maintenance is equally important. Damper isolator, structural connection, emergency generator, and evacuation system must be checked frequently. After a major earthquake, engineering should inspect buildings before people are allowed to return because some form of damage may be hidden. Each country should create and enforce earthquake-resistant construction standards based on its own geological conditions. High-risk areas must pay special attention to material quality, construction methods, structural design, and evacuation planning. Good engineering design can still fail if workers use poor material or ignore technical requirements. The greatest lesson is that earthquake safety is a completely system. Design, material, construction quality, maintenance, emergency preparation, and public education must all work together to protect human life. Part 13. Conclusion from Taipei 101 and Tokyo Skyscraper to Mirror and Shanghai Tower. Famous earthquake-resistant structures use different technology to deal with powerful natural forces. Taipei's 101 uses a massive steel frame to reduce weighing. Tokyo's Skyscraper rely on special central column inspired traditional Japanese pagoda. Other buildings use damping system, flexible steel frame, reinforced concrete wall, deep foundation, or base isolation devices. Although their designs are different, these buildings share the same fundamental principle. They do not attempt to resist every movement with complete rigidity. Instead, they are designed to move in controlled way, absorb seismic energy, distribute forces, and protect their most important structure or component. This approach makes building safer because control flexibility is often more effective than extreme strictness. A flexible frame can bend without suddenly breaking, while damper and isolators can reduce the amount of force acting on the structure. Strong foundation and carefully designed connections allow the building to behave as one complete system. Earthquake-resistant buildings are among the greatest achievements of modern architecture and civil engineering. They demonstrate the intelligence, creativity, and technical ability of humans to adapt to dangerous natural environments. More importantly, they protect millions of people who live and work in earthquake-prone regions. In the future, new materials, smart sensors, artificial intelligence, and advanced monitoring systems will make building even safer. Structures may be able to detect damage, adjust their response during earthquake, repair small cracks, or use releasable components to reduce recovery time. Earthquakes cannot be prevented, but their destructive effect can be greatly reduced. Through responsible construction, modern technology, strong regulation, and continuous maintenance, cities can become more resilient. Earthquake-resistant architecture is therefore not only an engineering achievement but also a central investment in human safety and the future urban life.